So when two events occur in sequence, we use the multiplication rule. All right, so the multiplication rule says the probability of A and B is equal to the probability of A times the probability of B given A just happened. I think of it sequencing in time, okay? So I think of A and B as the first and second thing, okay, to happen. All right, so I literally read this like the probability of the first thing happening times the probability of the second thing happen given the first thing just happened, okay? So it's like the probability, so say I want to find the probability of making the first free throw and the second free throw. It's equal to the probability of making the first free throw times the probability of making the second free throw given I just made the first free throw, okay? This scenario is played out when the events are dependent. Dependent events right here, okay? And it actually comes from the definition of probability of B given A, which we define to be P of A and B divided by the probability of A. How do you get it? You literally multiply both sides by probability of A, and then you see how it's the same as the multiplication rule right there, okay? All right. So the probability of A and B equals the probability of A times the probability of B. This is the rule if it's independent. Now, why does this work if it's independent? You think about it. If these are independent events, then the probability of B has the same chance of occurring as the probability of B given A just occurred. Okay? So the probability of B is equal to the probability of B given A if A and B are independent. All right? If they're independent, then this literally becomes that right there by definition of independence. All right? So two different formulas, so don't get confused when you see two different formulas. You need to know there's a difference. One's for dependent, one's for independent. All right? So let's do two examples. First one, two cards are selected without replacement. So without replacement means when we pick it up, we don't put it back. From the 52 card deck, find the probability of selecting a 7 and, key word here is and, a jack. The probability of selecting a 7 and a jack. So how's this different from previous problems? Earlier we were doing conditional probability where we said a 7 given a jack or a jack given a 7, right? The key word here is and. If I see the word and, I should think multiplication rule. That's the key word that tells me to use the multiplication rule is and here. So what is this equal to? Okay, so this is equal to, find the probability of drawing a 7 times the probability of drawing a jack given I just drew a 7. Okay, so the probability of drawing a 7 is 4 out of 52. And then multiply by the probability of drawing a jack, which is 4 out of, and then given I just drew a 7, that means there's one less card in the deck, so out of 51. And so that, my friends, is the probability there. Okay, and so when I do this, I get 16 out of 2652, which is roughly 0.006. And that is very unusual. All right, it's very unusual to be able to say, look, I'm going to draw a 7, then I'm going to draw a jack. That'd be pretty hard to do. Okay? Now flip a coin, and by the way, can't you see how these two things are dependent on each other? You see how they're dependent? Because drawing the 7 and not replacing it alters the probability of drawing the jack. Okay? Now, flipping a coin and then rolling a die. We determined that flipping a coin versus rolling the die, these two events are independent of each other. Rolling the coin has no effect on the probability of rolling the die. And so, therefore, the probability of rolling or tossing a heads and, keyword and tells me multiply, rolling a 2 is equal to the probability of rolling a heads times the probability of getting a 2. So that's 1/2, because there's 1 out of 2 possibilities. And then times 1/6, which is 1/12, or 0.083. Okay, if you had to round to 3 decimals. This is independent example, and this is a dependent events example. Okay?